Alright, we're back again with motion in one dimension. Last couple of videos, we've been going through these kinematic equations and figuring out how to choose which one to use in cases where only one equation is necessary. So I recommend you watch my past two videos called Motion in One Dimension, Part 1 and Part 2 before attempting this one. So I wrote the problem myself because I wanted to find some problem that for sure would take two equations. So it's kind of a silly problem, but it's a mathematical problem. So I'll read it now. It says a car is traveling at 25 meters per second. We don't know what speed it started at, but it has traveled 600 meters in 30 seconds. Assuming constant acceleration, calculate the acceleration and find what speed the car started at when the timer was started. So essentially we have some guy with a stopwatch. Car comes by, guy starts a stopwatch, but doesn't have a radar gun, so that they don't know what the initial velocity was. But they do know the distance between where the stopwatch was started and where the speed of the car was measured. That distance is 600 meters, and at the end of the thing, when they measured the car's velocity, they found it was 25 meters per second. And the timer guy knew when to turn off the timer, so it was 30 seconds. So reading this problem again, a car is traveling at 25 meters per second. So we know that its velocity final is 25 meters per second. I'm sorry, we don't necessarily know that that's v final until the next statement. We don't know what speed it started at. So that means that v initial is a big question mark. But it has traveled 600 meters, so that means that delta x is 600 meters in 30 seconds, so time is 30 seconds. Assuming constant acceleration, which is all these kinematics equations we have written up here do assume constant acceleration, calculate the acceleration. Alright, calculate the acceleration, question mark. And find what speed the car started at when the timer was started. So that's the initial. So we have two unknowns. You might have a problem that just asks you for the acceleration, or a problem that just asks you for the initial velocity. I decided to ask for both. So in this case, we look through some of our equations. We have, let's go ahead and go through these one by one. Alright, so we're going to start on the bottom. V initial is one unknown here. V final is one known here. T is unknown here. And X is also known. So here we have we have three knowns. V final, T, and X, three knowns, and one unknown. Oh, so interesting. This actually wasn't the way that I solved the problem, but it looks like this equation is a good lead. So let's go ahead and work it both ways, starting with the way I intended. Alright, so we look at this. We don't have acceleration, there's one unknown. We do have time, one known. V initial we don't know, two unknowns. Delta x we have, so this would be two knowns, two unknowns. Alright, next problem up, or next equation up. We don't have acceleration, we don't have v initial, but we do have v final and delta x. So that's two knowns, two unknowns. And then up at this equation, we don't know acceleration, we do not know v initial, but we do know time and v final. So once again, we have two knowns and two unknowns. Boy, you know, I kind of picked a lousy problem for showing how to know which equations to choose. But with this problem, it looks like there's a myriad of good choices. The choice I intended to make with this video was to use these two equations. So let's go ahead and do it that way. And then I think it would be cool to use this equation too, because that's going to solve for one of our unknowns, and then open up another equation. But I wanted to show how to work with two equations at the same time. So we start up here. We've got AT plus VI equals VF. So A t, we know time is 30 seconds. By the way, the past couple of videos I've been using units. Now that you've seen them work out, I'm just going to write numbers down because these problems are significantly longer, so carrying the units could take a while. So AT plus VI, we don't know VI, it's an unknown, equals VF. We do know VF, it's 25 meters per second. Alright, our next equation, 2A delta x, 2A, we don't know A. We do know delta x though, it's 600 meters, equals VF squared, that's 25 meters per second squared, minus VI squared, and we do not know VI. Alright, so we have two equations, two unknowns, and we're going to learn how to use substitution to solve this system of equations. There are several ways to solve systems of equations like this. You can look into elimination methods. You probably learned that in algebra class, and maybe someday, or maybe you already have learned about Gauss-Jordan elimination, which is kind of a cool way to use matrices that you may want to look into. They tend to make the problems more systematic. But for now, we're just going to use substitution. So let's rewrite these. We have 30A plus VI equals 25. I'm rewriting the first equation. Let's go ahead and solve for VI in terms of A. So VI equals 25. I could minus 30A over minus 30A. And now I have VI in terms of A. So where I have VI up here, let's plug in my A terms to this equation. So now this equation we have 2A times 600. Let's go ahead and simplify that now. We'll say 600 times 2 is 1200. A equals, what is 25 squared? Is it 625? It is. Cool. So 625 minus VI squared. Well, VI is 25 minus 30A. 25 minus 30A squared. So this is going to be a little bit intensive because we're just going to have to FOIL this out. So if you remember foiling, if this is squared, it means it's multiplied into itself twice. So that squared sign is the same as writing two terms multiplied by each other. So FOIL, we go first, outer, inner, last for terms. So the first 25 times 30, 25 times 30, A is 7, oh wait, I'm sorry, first is 25 times 25. 25 times 25 is 625. 25 times 30, 25 times minus 30A is minus 750A. Negative 30A times 25A is also minus 750A. And negative 30A times negative 30A is positive 900A squared. Alright, so, and we do not want to forget that this minus sign right here needs to be distributed into all these terms. Alright, so now the next step is to distribute the minus sign. So minus the 625 is minus 625. A minus times a minus is a positive. Minus times minus is positive. Positive times minus is a negative. So now we've distributed that minus sign. You'll notice the 625s cancel. The 750A's can add together to give us 1500A minus 900A squared equals, over here we have 1200A. Alright, so we can combine the like terms of A and A. So let's subtract 1500 from 1200. 1200A minus 1500A is negative 300A. So negative 300A equals negative 900A squared. Well, the minus signs cancel. We can divide by a minus 1 on both sides. We can divide both sides by A. a squared divided by a is just a. So we just have an a here. And a divided by a is 1. So then we can divide 900 by both sides. 900. So 300 over 900 is equal to a. Well, we can simplify that fraction and say that a is equal to 1/3. I believe that's what it is. 300 divided by 900 is 1/3 meters per second squared. So there's the first step of our problem. Now what we can go ahead and do is we can go back and plug in for a and solve for VI. So let's use this equation, 30a plus VI equals 25. Well, now that we know that a is 1/3, 30 times 1/3 is 10, plus VI equals 25 minus 10 both sides, and we end up with VI equals 15 meters per second. So we've effectively solved this problem using these two equations, and we use them jointly, which means we use the equations at the same time and to use substitution. But another way to do it, which I didn't realize was going to happen, is to use this equation first. So let's see if we can make that work. Let's remember that a, so 1/3 and 15. A is 1/3 meters per second squared, and V initial is 15 meters per second. But we don't know that at this point because we're going to resolve it, so I'll circle them in red. I just want to be able to double check our answers. So let's go ahead and start off using this equation because there's only one unknown. So we don't know VI, so VI plus, well, VF is 25 meters per second, divide 2 times T, which was given as 30 seconds, equals delta X, which was given as 600 meters. So we've used this equation, we've plugged and chugged. Well, actually we've plugged, now we're chugging. So 300, or 30 times 600, 30, or I'm sorry, divide both sides by 30. 600 divided 30 is 20. So 20 equals VI plus 25 divided 2. So we can multiply both sides by 2, which gives us 40 on this side, and then we can subtract 25 minus 25. 40 minus 25 equals 15, which is VI, so 15 meters per second. That was a lot quicker to get us to our first answer, wasn't it? The last one, because we were doing it jointly at the same time, as opposed to like sequentially, it definitely took a little bit more algebra. This way may just actually be the right way to do it. And when I say the right way, I mean the easiest way. There's plenty of right ways to do problems. So VI, now that we know VI, we just need to solve for acceleration. So we know, let's see here, well, if we know VI and VF and T, then acceleration is cake with this equation. So acceleration we don't know, times time was given as 30 seconds, plus VI we solved for as 15 meters per second, equals VF, which we know from the problem is 25 meters per second. So 25 minus 15, get the 15 over here, we end up with this equaling 10, divide by 30 on both sides, and what you end up with is A is equal to 1/3 meters per second squared. So that's perfect. We got the same answer. It was a heck of a lot quicker. So I think I just proved a good point. I went into this problem, I designed this problem to use these two equations jointly, but when I took a second look at it, I found an easier way to do it. So always be sure to look to see if maybe you have an equation with only one unknown before you start doing what I did the first time through. So anyways, I hope this was a helpful learning experience. I know it was for me, and I'll see you next time.